Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS Group. Today I will discuss about Laplace transformation. Laplace transforms. So Laplace transform method provide easy and effective ways for the solution of many problems arising in various fields of science and technology. Because of this, the theory of Laplace transform has recently become an important part of the mathematical background required by engineers, physicists and other scientists. This chapter has 3 articles and begins with definition and contains several theorems, formula of Laplace transform. So first I will start with definition of Laplace transform. Definition of Laplace transform. So let ft be a function for t greater than 0. Then L of ft equal to integration 0 to infinity e to the power minus st ft dt, okay, is called Laplace transform of ft, where the parameter s is positive and real. In some book you can find the parameter as written as p. So if the above this improper integral does not exist, we say that Laplace transform of ft does not exist. Okay, so we denote this Laplace transform of ft by fs, since this will be a function of s. Okay, now to Laplace transform we can use we have to use the definitions, but after reducing some formula, basic Laplace transform of some basic function, we will use them to transform to get Laplace transform of some composite functions. Okay, so first let us take ft equal to 1, that is capital ft equal to 1. So we will find the Laplace transform of 1. Okay, so by definition L of 1 will be 0 to infinity e to the power minus st, here ft is 1, so dt. Okay, now we are using since this is an improper integral, so limit x tends to infinity 0 to x e to the power minus st dt, and equal to limit x tends to infinity, this will be 1 by minus s e to the power minus st 0 to x, limit x tends to infinity minus 1 by s, and this will be e to the power minus sx minus, it will be 1 after putting t equal to 0, so minus 1 by s limit x tends to infinity e to the power minus sx minus 1, and since x is tending to infinity and this is tending to minus infinity, it will be 0, so minus 1 by s into minus 1, that will be 1 by s. So L of, that is Laplace transform of 1 is 1 by s. Okay, so if L of 1 is 1 by s, then L of 2 will be 2 by s, that is L of c will be c by s. This is a property, I will discuss it later. L of any constant, arbitrary constant, c is an arbitrary constant, L of c will be c by s. Okay, so you have to remind it. Next, I will find the Laplace transform of t to the power n. Okay, so L of t to the power n. Okay, by definition we can write that 0 integration 0 to infinity e to the power minus st t to the power n dt. So now we'll perform by parts integration to integrate this function. So it will be t to the power n e to the power minus st. Okay, first since this is an improper integral, limit x tends to infinity 0 to x e to the power minus st t to the power n dt. Now limit x tends to infinity t to the power n to integration of second function, that is minus s, minus integration differentiation of first function, that will be n t to the power n minus 1, and it will be plus 1 by s e to the power minus st dt. Okay, so it is 0 to x, it is 0 to x. Now after putting a limit here 0 to x, for x, since x is tending to infinity, it will be tending to minus infinity, so for x this will be 0, and for 0 this will also be 0 because there is t to the power n. So the remaining part is limit x tends to infinity 1 by s, n by s, sorry, n is also constant, 0 to x t to the power n minus 1 e to the power minus st dt. Okay, so now n by s, here I am putting again infinity in place of x, that will be 0 to infinity t to the power n minus 1 e to the power minus st dt. Okay, so this is also a definition of Laplace transform of which function? L of t to the power n minus 1. So in this way, if we continue this by parts integration or Laplace transforming by definition, next we will get n into n minus 1 by s square into L of t to the power n minus 2, and it will be continued so on. So finally we will get n factorial by s to the power n plus 1. Okay, n factorial by s to the power n plus 1. So Laplace transform of t to the power n is n factorial by s to the power n plus 1. Okay, so now we can apply this result for various powers of t, that is if we take L of, okay, if we take L of t cube, that will be here n is 3, that will be 3 factorial by s to the power 4, that is 6 by s to the power 4. So if you, it is only for integer when n is an integer, and when n will be fraction there is another result. So if you put any integer in place of n, you will get the Laplace transform of L of t to the power n for that integer. Okay, now since we know that gamma n plus 1 equal to n factorial, in place of n factorial we can also write gamma n plus 1 by s to the power n plus 1. So we can use this result gamma n plus 1 in place of n factorial when n will be a fraction, since factorial of fraction does not exist. So when n will be an integer, we have to use this result. When n will be a fraction, we have to use this result. Okay, now I'll go to next result. Okay, so the next result is L of e to the power at is equal to 1 by s minus a. So now I will write only the results, basic Laplace transform of some basic functions which we can use to find the Laplace transform of some composite function. So this result I'm not showing the proof. You will prove this using definition, like I did just the two examples of Laplace transform of a constant and Laplace transform of t to the power n. So in that way you can find these results. Okay, so I am not showing here, I am just writing the results. So I am writing all the results from first. So L of 1 is 1 by s, number 1. L of t to the power n is n factorial by s to the power n plus 1, or you can use gamma n plus 1 by s to the power n plus 1. This will depends on the value of n, whether it is an integer or a fraction. Now next, L of e to the power at will be 1 by s minus a. Number 4, L of sin at, it will be a by a square plus a square. Number 5, L of cos at, L means Laplace transform, so s by s square plus a square. Number 6, L of sin hyperbolic at, that will be a by a square minus a square. Number 7, L of cos hyperbolic at, that will be s by a square minus a square. Okay, so these are the basic Laplace basic results of some Laplace transformation of some basic functions. Now we will discuss some properties of Laplace transform which are very important to solve problems of Laplace transforms. Okay, so first property I will write. Okay, I am removing this. The first property is linear property of Laplace transform, LT. Okay, so L stands for Laplace and T for transform. I am not writing the full form. So the property is Laplace transform of C1 F1t plus C2 F2t will be equal to C1 L of F1t plus C2 L of F2t. So now I'll prove this. So LHS, that is L of C1 F1t plus L of C2 F2t, will be equal to, by definition, applying the definition of Laplace transform, we will get 0 to infinity, integration 0 to infinity e to the power minus st into this function C1 F1t plus C2 F2t dt. Okay, now by using the linear property of integration, we can write by multiplying C1 integration 0 to infinity e to the power minus st F1t dt plus C2 integration 0 to infinity e to the power minus st F2t dt. Okay, so this will be equal to C1 into Laplace transform of F1t by definition of Laplace transform plus C2 Laplace transform of F2t. It is also by definition. So here the proof of linear property of Laplace transform. Okay, next before going to next property, I'll give you some an example of linearity property. Suppose we have to find L of 5t cube plus 3 cos 2t plus 7 e to the power minus t. Okay, so by applying linearity property, you can write 5L of t cube plus 3L of cos 2t plus 7L of e to the power minus t. Now I have discussed the previous results of Laplace transform of t to the power n. That will be n factorial, that is 3 factorial by s to the power n plus 1, that is 3 plus 1 plus 3 into Laplace transform of cos at is s by a square plus a square, here a equal to 2, plus 7, and Laplace transform of e to the power minus at is 1 by s minus a, here a is minus 1, that is coefficient of t, that will be plus 1. So you have to remind all the basic results I wrote here always when you are solving a problem of Laplace transform. So this will be 30 by s to the power 4 plus 3s by s square plus 4 plus 7 by s plus 1. So this is the example of linear property of Laplace transform. Okay. Now I'll go to first shifting property, and which is very important and very useful. First shifting property. So this property states that if L of ft equal to fs, then L of e to the power at ft will be f of s minus a. Okay. So when a function is multiplied by exponential function, it will be changed from fs to fs minus a. Okay. So the proof of this function of this theorem can be given to you by like this, L of e to the power at ft. Okay. So by definition it will be integration 0 to infinity e to the power minus st. Ft means e to the power at ft dt, and this is equal to 0 to infinity e to the power minus s minus a into t ft dt, and by definition of Laplace transform it is here you can see that the parameter is s minus a, so it will be function of s minus a after Laplace transformation. So here is the proof. Now I am going to examples of first shifting property. Let us find L of e to the power minus 5t sine 2t. Okay. So here you can also find it by definition, but if you use first shifting property it will be easier. Okay, and less time will be needed. Okay, so first here you see that if you compare this by with the first shifting property, here e to the power at ft, here e to the power at is e to the power minus 5t and ft is sine 2t. So we know okay, first we write here ft equal to sine 2t, and we know that L of ft, that is L of sine 2t, L of sine 2t is 2 by s square plus 4. Okay, so this is the function fs, this. Okay, now this sine 2t has been multiplied by e to the power at, that is e to the power minus 5t. So what will be the result of Laplace transform? It will be fs minus a instead of fs. So here our fs is 2 by s square plus 4, and a is this minus 5 coefficient of t in the exponential function. So it will be 2 by s minus a, that is s minus 5. So this will be s plus 5 whole square plus 4, and after simplifying this will be s square plus 10s plus 25 plus 4, 29. So this is the result of a Laplace transform e to the power minus 5t into sine 2t. So this was an example of first shifting property. Now I am going to second shifting property. Okay. Okay. Second shifting property. So second shifting property states that if L of ft is fs and gt equal to f of t minus a when t greater than a and 0 when t less than a, then L of gt will be e to the power minus as fs. So this is the statement of second shifting property. Let's take an example of second shifting property, of application of second shifting property. So the question is find L of ft where ft is defined as ft equal to cos of t minus 2 pi by 3 where t greater than 2 pi by 3 and 0 when t less than 2 pi by 3. Okay, so here you can see that this function ft is in the form of gt, that is f of t minus a where a is 2 pi by 3. So comparing with the statement, we can say that this is the function gt and then ft will be cos t. Okay, so L of cos t, we know L of cos t is s by a square plus 1. Okay, so this is our fs. Now if we want to find the Laplace transform of this function, this will be fs multiplied by e to the power minus a. Simple. So L of ft will be e to the power minus as, so that a is 2 pi by 3 here, so minus 2 pi by 3 s into fs, that is s by a square plus 1. Okay, so second shifting property, this was an example of second shifting property. Okay, now next property is change of scale property. Change of scale property. Change of scale property. This property is also very important. The statement of this property is if L of ft equal to fs, then L of fat will be 1 by a f of s by a. Okay, so this is called a change of scale property, and the proof of this theorem is, so L of fat by definition of Laplace transform, we can say integration 0 to infinity e to the power minus st f of at dt. Now we substitute at by z, then a dt equal to dz. Now substituting 0 to infinity e to the power minus s, t will be z by a, t will be z by a f of z, dt is 1 by a dz. So here we can write this as 1 by a integration 0 to infinity e to the power minus s by a z fz dz. So this is definition of Laplace transform of fz, and the parameter is s by a. So it will be 1 by a f of s by a by definition. Okay. So this is the proof of change of scale property. Now I'll give you an example of change of scale property. So I'll give you two examples to make you understand better. First example is, if L of some function ft, function is not given, Laplace transform of ft is given. L of ft is s plus 1 by s square plus 3s minus 1. Then find L of f 3t. So it is clear that we have to use change of scale property because t has been multiplied by a constant a. Okay, and here a is 3. So simply L of f3t will be, so this is our fs. Okay, so 1 by a into f of s by a, just 1 by 3, a is 3, and fs will be f of s by a, that is we have to write s by 3 in place of s. So s square by 9 plus s by 3, 3s by 9, that is, okay, no, 3s by 3 will be s plus 1. So it will be 1 by 3 into s plus 3 by 3, and it will be s square plus 9s plus 9 by 9, and that is equal to 1, this will be 9 by 3. So 3 will be cancelled. So s plus 3 by s square plus 9s plus 9. So this is one example of change of scale property. Now I will give you another example. Suppose we the question is we have to find L of cos 3t using change of scale property. So we know what is Laplace transform of cos 3t. We know the basic result which we have already found out by applying definition. But if it is asked to find L of cos 3t using change of scale property, then how to do? So L of cos 3t, if we consider cos t, then L of cos t is s by s square plus 1. Okay, so this is our ft, that is original function, and this is fs. Now this t has been multiplied by 3, that is a is 3. So L of cos 3t will be, now we can apply change of scale property. It will be 1 by 3, 1 by a, f of s by a, that is s by 3 into s square plus 9 plus 1. So this will be s by s square plus 9. So here is the Laplace transform of cos 3t which we have found out by applying change of scale property. Okay. Now I'll go to next property, and the next property is Laplace transform of some function of derivative of a function. Okay, derivative of a function. Okay. Okay, so Laplace transform of derivative. Laplace transform of derivative. So the statement is, if L of ft equal to fs, then L of f dash t equal to s fs minus f0. Next, this is the first order derivative of ft. L of f double dash t will be s square fs minus s f0 minus f dashed 0. Okay, and in this way the Laplace transform of nth order derivative will be L of f nt equal to s to the power n fs minus s f0, sorry, s to the power n minus 1 f0 minus s to the power n minus 2 f dash 0 minus dot 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 up to f n minus 1 0. Okay. Now I'll go to some examples. We have to show that L of sine at is equal to a by a square plus a square using Laplace transform of derivative. Okay. Although we know we can do this by change of scale property, or we can do this by definition. Now I will do it by Laplace transform of derivative, property of Laplace transform of derivative. Now here ft equal to sine at, and L of ft is equal to fs. Okay. Okay, I will do it by using second order derivative of Laplace transform of second order derivative. Now f dash t is equal to a cos at, and f double dash t is minus a square sin at. Okay. Now we know that L of f double dash t is a square fs minus s f0 minus f dash 0. Okay. So L of f double dash t is minus a square sin at, and we don't know what is fs. Okay, we have to prove this. So a square we are writing as fs minus f0, that is the value of sin at t equal to 0, it will be 0, and minus f dash 0 means the value of this function at t equal to 0, this will be a. Okay, so from this we can write minus a square L of sin at, L of sin at is equal to a square, and fs means also L of sin at minus a. So here by solving this, if we find the value of L sin at, it will be a square, okay, minus a by minus of a square plus a square, that is a by a square plus a square. So this is the Laplace transform of sin at, a by a square plus a square, which you already know, but now we have done it using Laplace transform of second order derivative function. Okay. Now next property I will go, Laplace transform of integrals. Laplace transform of integrals. Laplace transform of integrals. This property states that if L of ft equal to fs, if L of ft equal to fs, and ft satisfies the following conditions. Ft satisfies the following conditions. Number 1, ft and f dash t are continuous on 0 to n, and number 2 is there exists some real number capital M and v such that mod of ft less than m e to the power m e to the power vt, and mod of f dash t less than m of e to the power vt. Okay, and number 3, okay, sorry, the statement, these conditions should not follow. I have done some mistake. It will be if L of ft equal to fs, then L of integration 0 to t fx dx will be 1 by s fs. Okay, will be fs. Okay. Now for an example, let us take if L of, we have to find L of integration 0 to t to the power t cos 2t dt. Okay, now you see that here this form is similar to this form. Here the function ft is e to the power t cos 2t. Now we know that L of cos 2t is s by s square plus 4. Now by applying change of first shifting property, we can find L of e to the power t cos 2t, and that will be s minus 1 by s minus 1 whole square plus 4, and that will be s minus 1 by s square minus 2s plus 5. Okay, so this is the Laplace transform of L of e to the power t cos 2t. Now it is being integrated from 0 to t, and Laplace transform of this function, that is L of integration 0 to t e to the power t cos 2t dt will be equal to 1 by s, this is fs, this is our fs, 1 by s fs, that is s minus 1 by s into s square minus 2s plus 5. Okay, so this was the property of Laplace transform of integrals. And next, many more properties. There are many more properties of Laplace transform, and we'll do this. We'll show you in the next video. In this video, that's all. You have to you will watch this video, and if you face any problem or if you have any query, you can contact with me. My contact details is given in the first slide of this video, and you have to practice this type of problems, otherwise it will be not clear to you. Today I have discussed about linear property, first shifting property, second shifting property, change of scale property, and Laplace transform, derivative, and integrals. So the 6 properties, and there are near about more 3 to 4 properties of Laplace transform. In the next video I will discuss that, and I will solve some problems of Laplace transforms, and then I will go to inverse Laplace transform. So watch this video. If you have any query or problems, you can contact with me. My contact details is given in the first slide of this video. Thank you.